Hello. Well, thanks for the introduction, and thanks to Sylvie and the team for inviting me to give this seminar. I'm very much looking forward to it. So it's about the question whether we should abolish statistical significance. And we'll start with the first statistical hypothesis test in history, as far as we know, which was done by this man, John Arbuthnot, who lived at a time when scientists could aspire to have some sort of knowledge about all the sciences. And he was also, like many scientists, well, maybe all European scientists of his time, he thought the purpose of science is to understand the plan of God for his creation. So that was his idea. And the way he tells the story is that he observed that in his time, sort of the late 17th, early 18th century, that young men and boys were more likely to die early in their life before they could marry than girls and young women. And so he says that should create an imbalance whereby there should be more women of marriageable age than men, and that in his in his thought wouldn't be a perfect world, because then there wouldn't be one man for every woman. So he thought maybe God has thought about this too. And so the way he tells the story is that he analyzed 82 years of London birth statistics, and he looked at how many girls and boys were born in each of these 82 years. And he found that in all 82 years, there were more boys than girls recorded as having been born. And so his hypothesis test was this. He assumed, well, under the null hypothesis that male and that a child is equally likely to be born male or female, the probability to observe more boys than girls in all of 82 years is this. So if boys and girls are equally likely, then the probability of having more boys than girls in 1 year is about a half. And for that to happen 82 years in a row, it would be 1/2 to the power of 82. And that gives this probability here. And that, as far as we know, is the first p-value that someone has calculated on real data. So this p-value is very small. And so Arbuthnot didn't call it a p-value, but he did say, from this result, it follows that it is art, not chance, that governs. Today, people would pretty much say the same thing by saying, well, p is smaller than 0.05, so the result is statistically significant. And Arbuthnot's interpretation was that this shows that God has had a hand in determining the sex of a baby to ensure that by the time people are of marriageable age, there's equal numbers of males and females. So this was, as far as we know, the first hypothesis test. It shows that a test can be useful in the sense that that is actually an interesting question. Is a child more likely to be a boy or a girl? Is the probability equal or not? But it also maybe shows the shortcomings of statistical hypothesis tests. So first of all, Arbuthnot, I think he probably didn't start with the data. He probably started with a theory that, divine intervention is his theory. But although he calculated probability, this is not the probability of his theory being true or his theory being false. The probability of his theory being right is entirely unclear from this analysis. Also, if he thought that there's divine intervention, he could have actually done something more interesting, which is he could try to predict specifically how many boys, how many more boys than girls he should be born if he is right, and if at the age of that he considers the marriage age, there were actually equal numbers of young women and men left. He didn't look at that. He also didn't use his data to estimate the male-female birth ratio, which is actually an interesting number. Today, we know that that's about 1.05, so about 5% more boys than girls are born biologically. And that can be used in social science. So, for example, in some times and in some regions of the world, this 1.05 value is not what you find in the data, and that might be evidence for sex selection based on prenatal sex determination and abortion. So you can actually use this biological constant or estimate of a biological constant to say something about societies. So Mr. Arbuthnot did not do that. And he also didn't consider alternative explanations for his findings. And today, the use of significance tests today sometimes has the same limitations. So imagine, for example, Charles Darwin had said, there's evidence against the idea that all species were created fully formed, p smaller than 0.05, and he hadn't given us any evidence for his idea of evolution. We would think that a rather more poorer account of his theory of evolution than the account he actually gave, which is lots of evidence for evolution happening. You know, all the finches, the transitionary fossils, and so forth. So just to say, before I go and question statistical significance as a concept, I just want to say from the outset that I do think hypothesis tests can be useful. So the basic idea is that you put your theories to the test of data, taking account of random variation that might also be in the data. And so you ask yourself, if my theory is right, what would I expect to see in the data, and what would I need the data to look like in order for me to say my theory is probably wrong? And so this is the basic principle, and statistical tests can help to give us a gauge in, you know, how whether the data are compatible with a certain theory, or whether they are they're incompatible with a certain theory. So part two then, there has recently been a lot of debates about statistical significance. The debate itself is not new, but it has intensified in recent years. In 2019, a special issue of the American Statistician published no fewer than 43 articles about reforms in the use of statistical hypothesis tests in science. And one of them, by very distinguished authors, suggested to abandon statistical significance altogether. Not all 43 articles made that suggestion, but they're all suggested reforms of the current use of statistical hypothesis tests. A little bit earlier in 2015, a psychology journal, Basic and Applied Social Psychology, went even further and said they won't publish any manuscripts that had p-values in them. So if you submitted an article to them with p-values in it, the best outcome would be that they'd send it back and say, well, this is fine, but remove all the p-values. So there have not been p-values published in this journal since 2015. Now, this report on that journal is from the journal Nature. And the interesting thing is that Nature, one of the top 2 science journals in the world, when they wrote about this article, they themselves didn't actually define correctly what a p-value is. They, the person who wrote this up made a mistake in how they describe what a p-value is. And they said the closer to 0 the p-value gets, the greater the chance the null hypothesis is false. This is not correct. The p-value is not the probability that the null hypothesis is false. It's the probability of the data under the assumption the null hypothesis is right. So this maybe illustrates an important thing, an important part of the story, which is that p-values and statistical significance are quite widely misunderstood. among people that do applied research, including very eminent people. So some of the most common ones, misunderstandings, are that there is a confusion between statistical significance, so which is about the data being incompatible with some null hypothesis, and scientific or clinical importance, such as the effect of a medication has a tangible benefit for patients. So these two are certainly not the same. A small p-value, or by convention smaller than 0.05, is often mistakenly interpreted as proof of an effect. Most people know that this is not literally true, but anyway, write as if it was true. Even more common is to interpret a large p-value, by convention larger than 0.05, as proof of absence of an effect. So how often have I read a paper or a draft of a paper where somebody, for example, had observed a correlation of, say, 0.3, so a smallish correlation, but still noticeable, but the p-value was large, 0.2 say, and they said there was no association between X and Y. This is not correct. If you've observed a correlation, then there was an association in your data. The question is, how confident can you be that this association is also, generally exists in the population? But certainly you haven't shown that there's no association just because you've observed a large p-value. Also, there's a sort of lack of imagination, or maybe a sort of conventional rigidity about which null hypotheses are worth testing. It is not the case that it necessarily has to be, the null hypothesis has to specify no effect or absence of relationship or no difference. And then there's a widespread failure to recognize the conditions under which hypothesis tests actually are valid indicators of anything. And I'll come back to that later on in my talk. So before I go more into sort of uses and misuses of significance tests in research practice today, I want to link another debate into the mix. And this is the debate about a potential crisis of replication. So an important paper in this debate was this one here from 2005, John Ioannidis, who claimed that most published research findings are false. And the hunt for statistical significance in a field was one of the things he identified as responsible for the fact that many published research findings that you find, in the literature that are cited, often cited repeatedly, are actually false. Before I go more into this idea of published findings being false, I want to introduce some definitions, because there are some terms that are used sometimes in a confusing way. So I make a distinction between reproducibility or reproduction and replication. So if you're trying to reproduce a finding of an original study, I define that as you're using the same data, trying to use the same method and try to come up with the same result. So you actually get the data from the original study and try to reproduce exactly the analysis that they did. And this can sometimes fail when people have, for example, made up their data or have not documented their methods precisely enough for someone else to actually come to the same results and reproduce the same analysis. So replication is something stronger. Replication is if you do a new study and trying to see whether your new study finds results compatible with the original study. So, and within that, I would distinguish direct replication, which is you collect new data, but you use the same methods as the original study, and you're checking, do I find the same results or similar results as the original study? And the other type is conceptual replication, where you research the same question as the original study, but you're collecting new data and you use different methods. So a classical example of that is some results have been published based on observational studies, say analysis of clinical records, and you try to confirm the result from those studies using a randomized controlled trial. So they're using a different method, but you're assessing the same question, is substance X, Y, or Z protective against disease A, B, or C? So I thought that was important to say, because sometimes reproducibility or reproduction is used in the sense of replication. But I think it's important to keep these apart. So there has then been talk of a crisis of replication in the sense that it's been observed anecdotally that quite often when people have tried to replicate a result, a published result, that they found they came to different conclusions in their replication study. And so there have been some formal attempts to assess the degree to which results published in certain scientific fields are replicable. So in psychology and social science, they did large-scale replication cluster attempts of that kind, and found that on average the effect sizes in the replication studies were much smaller than in the original studies, and between about between about a half and 2/3 of the original study could be replicated, in the sense that the results were compatible with one another. There could be a whole other talk about what actually counts as you have replicated the original result, because you're unlikely to find exactly the same result, but what counts as a compatible result of a replication. But yeah, but roughly between half and 2/3 of these studies were replicated in the sense that compatible results were found. So a considerable proportion were not replicated. And in epidemiology and public health, the debate is often about the reliability of results from observational studies. And there have been several high-profile examples where randomized controlled trials have challenged previous conclusions based on many observational studies. So for example, with the effect of antioxidant vitamins and also workplace well-being programs. So both of these seemed beneficial from observational studies, but less so from when you looked at RCTs. There is a debate, though, about whether the failure to replicate some scientific results actually should be called a crisis, because research is not about always finding the truth. Research is about incremental progress towards a better understanding. And so if somebody published a well-conducted study, but the result is later found to be to not hold up to further evidence, that's not necessarily indication that the original study was wrong in any way. This is part of the progress of science. And we shouldn't trust the result, almost any result, that's just based on a single study. So you need several studies looking at a problem from several angles, taking into account many sources of evidence before you come to a scientific consensus. So this should be the normal progress of science. But in practice, is it always done that way? And so I want to illustrate the importance of conducting replication in two cautionary tales. The first is the cautionary tale about power poses. So here we have Wonder Woman, in the background, and in the foreground is Amy Cuddy, who was one of the authors of a psychological study on power poses. So power poses are physical postures that you take up that look powerful, such as the one demonstrated here, but in the study there were actually slightly different poses that they checked, that they tested. And so in that study, which was a small study, 42 participants, they randomized their participants to either telling them you have to hold a high power pose for 2 minutes, something like we saw in the picture, or the control group held a submissive pose or a low power pose, so something like being hunched in, looking at your own feet and so forth. And so they found at the end a difference between the groups. After 2 minutes of holding these poses, the power pose group had measurably higher testosterone with a small p-value, 0.045. And so this was a surprising result. And as a consequence, then one of the authors, Amy Cuddy, who we saw in the picture, then created quite an elaborate theory of the importance of boosting your confidence and performance by holding certain power poses. And she also did a very popular TED talk. And so this power pose idea has entered sort of psychological folklore as something you can do to boost your confidence and performance. Now, there have been many replication attempts. And in 2017, a summary of these replications concluded that there is, on balance, no evidence for an effect of power posing on testosterone or indeed any hormones. So in general, this initial study is the only one that found an effect, a positive effect of these power poses of testosterone. And since then, I think about a dozen studies have failed to find that effect. So the important thing to know here is that there was nothing wrong methodologically with the initial study. It's not that they made a mistake in the methodology. The only mistake was to just take the single study, the result from the single study, and take it as established fact, without waiting for waiting for further confirmation, doing further research to back up this result. So this relates to what's demonstrated in this table here, which many of you might have shown when you first learned about statistical hypothesis tests, is that hypothesis tests never remove uncertainty. Because if you go with this dichotomization of evidence as in, small p-value, large p-value, either accept or not accept the null hypothesis, then whatever you do, there's always the risk that you can be wrong. So you can make, if you reject the null hypothesis, so in this example, they reject the null hypothesis that there is no effect of power posing on testosterone. So they concluded there is an effect. You can have a false positive. And if the p-value is large and you accept the null hypothesis, you might have a false negative. You might have failed to find an effect that's really there. So the important thing is there's always this risk that you're wrong. So your single study, based on a p-value, however large or small, doesn't remove uncertainty from your conclusion. So cautionary tale 2 is about the thing I already mentioned, which is about, can we trust the results of observational studies? So even very well conducted observational studies with very thorough analysis of potential biases in the data, controlling for many potential confounders and so forth. Everyone knows that, or most people know that in such observational studies there's always a risk that you have failed to control for some important confounders. So it's very difficult to claim causality from them. But when study after study shows the same thing that's often forgotten. And so in not too long ago, from observational studies, there seemed to be a pretty reliable consensus that vitamin C protected you against coronary heart disease. And the observational studies were showing moderately large benefits of vitamin C. But then when a clinical trial was done, this effect was not found. With pretty much high reliability, you could say that if there was any effect of vitamin C, it was likely to be very small, so small as to be clinically irrelevant. So if you focus on the p-value only as the measure of strength of evidence for finding anything, then that risks ignoring all the other things that we're all taught in Research Methods 101 are really important. For example, the related prior evidence, the plausibility of the biological mechanism, for example, or the social mechanism, the design of your study, the quality of the data, the confounders you've managed to measure and account for, and so forth. So all too often people home in on the p-value as the main thing that's important in judging how strong the evidence for or against something is. And that is really a mistake. And the article I showed earlier, which argued for abandoning statistical significance, says we really need a culture shift in how we judge strength of evidence, and the p-value shouldn't be the most prominent thing we report, for example, in an abstract. So now we come to the maybe what I think is a very large but very interesting question is whether the current use of statistical significance, so the current use of hypothesis tests, actually causes the publication of false results. So as I've said, I don't think we should necessarily abandon hypothesis tests completely, but I definitely think that current research practice does contribute to false results being published that don't need to be published. So there are 4 ways, at least, in which hypothesis tests currently are abused and contribute to the publication of false results. So there are publication bias, multiple testing, phishing for statistical significance, and research degrees of freedom. So publication bias results from the fact that statistically significant results are considered to be attractive, more attractive than findings that are not statistically significant. So journals like to publish papers that find something new and exciting, and most journals see statistically significance as required for claiming to have found something new. So that means that studies that have a statistically significant finding are more likely to get published than studies that haven't got such a finding. So if 10 researchers research the same thing, 9 find large p-values and 1 happens to find a small p-value, then this one study with a small p-value might be the only one that gets published. And so the published evidence looks like there is strong evidence in favor of whatever effect they're researching, but the 9 studies that show there's actually no evidence never see the light of day. So that creates what's called publication bias. Second threat, multiple tests and selective reporting. So if you have a large data set and you have, say, many different outcome variables that you're looking at, say, different diseases or different measures of psychological properties and so forth, then the more statistical tests you do, looking, for example, for group differences in this or the other outcome, the more likely you are to get a statistically significant result just by chance, even if there is no effect at all in reality or in the population. This has led to some quite bizarre results, which is was tested by a group of neuroscientists who did an fMRI study of a dead fish and showed this dead fish pictures of humans that human faces that displayed emotions, and they found that the salmon reacted statistically significantly to certain emotions more strongly than others. So how did they find this? Well, if you do an fMRI, even of a dead fish who has no brain activity, you have some noise in the data, you have some random variation in your measurements. And because you measure so many different brain regions, they're separated in voxels, which is a three-dimensional version of a pixel. If you test sufficiently many regions, then just by chance, you're likely to find some statistically significant results. So this dead fish fMRI analysis is a way to show that current methods to adjust for multiple testing at the time weren't adjusting in the right way, so that you still had this high risk of false positives due to multiple testing. Related but different is the practice of phishing for statistical significance. So this is actually if you try to be clever. If you are clever, you are almost guaranteed. So you can design your study so that you're almost guaranteed to get a statistical significant result. So you can do this by cherry picking. If you analyze a large data set, you test many different hypotheses, say 100 hypotheses, then on average, even if all these your research hypotheses are wrong, so all the null hypotheses are true, then on average, from 100 hypotheses, you find 5 statistically significant results. Now, if you then just select by p-value, so you only write up your the results that are statistically significant and claim in your research report that you had this hypothesis from the beginning and that lo and behold, your data have borne this out, it looks like you had a brilliant hypothesis, you've collected data to test it, and then your hypothesis was borne out. But this is using a small p-value to deceive your readers into thinking you have strong evidence for a hypothesis, when in fact you've just looked at random patterns in the data, identified the ones that happen to look attractive, and then wrote your research disguising that fact. So this is called phishing for statistical significance, or also p-value hacking. There is a journalist who did this on purpose and later revealed it as a hoax. And he did a real study, collected real data, and he found that eating chocolate helped. He found evidence that eating chocolate can help you lose weight. So losing weight was one of 18 outcomes, and he just picked the one for his report that happened to have a small p-value. And he did this to show how easy it is to get poor research into the media. They wrote a very attractive press release, and it got widely reported, depressingly always with the same kind of picture. So there was never a 60-year-old black man enjoying chocolate in the research, in the newspaper reports. And that's maybe all I need to say. So he revealed it as a spoof, and I recommend his article about this spoof. So phishing for statistical significance is a sort of label for a malicious practice intending to deceive, but the same thing can actually happen inadvertently. And this is, I think, something that is less often realized by researchers. Because in the course of an analysis, if you're not doing like a randomized controlled trial where you have to pre-specify every single thing you do, often when you're starting to analyze your data, whether you collected them or there were maybe available data that you managed to get permission to use. There are many small decisions that you need to make. So, which outliers to exclude, how to deal with your relations between variables. Should you transform some variables? Should you analyze everyone or just subgroups, and then which subgroups and so forth? And all these small decisions influence the result that you find. And now there is a temptation to analyze the data in many different ways, and in the end, maybe believe the result most that confirms the hypothesis that you had at the beginning. And so you could actually find yourself to be fishing for statistical significance without ever actually intending to do so. So this phenomenon is called researcher degrees of freedom. So the result of the analysis depends on researcher decisions, which are not necessarily scientifically clear-cut which decision you should make. It has also been referred to as the garden of walking paths because of this phenomenon. So, you make one decision, and depending on what you do, you face another decision and so forth. And so already by the time you've made 3 decisions, you might have 8 different ways of analyzing the data. And which one do you trust? This is actually, I'll skip this slide and go to the next one. It has actually been shown that this makes a difference. So there was an experiment done not too long ago where the authors gave the same data set to 29 research teams and asked them to investigate whether a football player's skin color is related to their risk of getting a red card. And so 29 teams obtained 29 different results based on the same data set and the same question, where the results were anything from there is a large skin color bias in giving red cards, like odds are 3 times higher for black players than white players, up to there is no or little or even a little bias in the opposite direction. And this is entirely dependent on analytic choices made in the analysis of the data. And so this is not the only case in which this has been found. In fMRI data, there was a similar experiment done and published last year. So this matters, and it's one reason why we need to do more to be open about the decisions we make in the course of analysis, which are currently often hidden in published manuscripts. Which leads me to the question of what can we do, and this is the final part of my presentation, and I know I'm dangerously close to overrunning, so I can assure you that I'm now coming to a close. So thinking about the implications of what I just said, so first of all, if you're in the position where you analyze your own data using your favorite statistical software, be it SPSS data or something else, the p-values that you get from your analyses, they look scientific, and they're given to you by default by the computer as if you always need to look at them, but these may be entirely meaningless because it depends on how you've conducted your study and analysis. So the p-value you get from your software might be total nonsense, even though when you then write up your study, people might accept and cite this p-value, people might accept it as good scientific practice, but it might actually be total nonsense. When you read publications, it's not always possible to tell from what they tell you about how they've done the research, how meaningful their p-values actually are, because of these hidden, for example, hidden researcher degrees of freedom that I've discussed. Misinterpretation of the meaning of p-values is common in publications. There's also an over-reliance on hypothesis tests over other statistical methods. So this relates back to Mr. Arbuthnot and his failure to estimate the sex ratio at birth. The p-value was all he gave mathematically. Why not estimate how many boys than girls are being born? And this dichotomization of statistical evidence via a threshold that defines statistical significance. So is it smaller than 0.05, smaller than 0.01? So this could be useful in some context. For example, when you want to set a threshold that a pharmaceutical company needs to demonstrate in order to claim that their medication works better than something else. But actually, in many contexts, this threshold is misleading and harmful if people then think either my study shows proof of an effect or it shows proof of an absence of an effect, rather than saying, well, this is a contribution to the body of evidence that we're accumulating. So several solutions to aspects of these difficulties have been proposed. One I mentioned already, which is transparency and open science. So make your data available if you can, make your materials available, such as questionnaires, make your statistical programming code available for everything you publish as far as you can without breaching confidentiality. This would be a strong, I mean, there should be a really strong push to do that every time you publish anything. There's the idea of registered research report, which is that you send to the journal a plan of your study before you have collected data. So you pre-register your study, and journals approve or reject them based on your study plan. So based on how important is the topic and how good is your methodology, not based on the results. So this avoids journals selecting statistically significant findings for publication and rejecting those that have no findings. In terms of observational studies, there are attempts, including here at UCL, to improve the design of the analysis. So one person to look for there is Bianca de Stabile, for example. Triangulation is back in the mix, again, also promoted at UCL by people much more eminent than me. So this is about researching the same question using two different methods, but in one study. So actually take the effort to, in a sense, do two studies and discuss the implications before you publish. And then in terms of analysis, there are ways to, such as bias analysis and sensitivity analysis, that deal with the researcher degrees of freedom. So trying it out different ways and see whether the results are robust to different analysis methods. So the main thing, and I said this at the outset, is to know that your statistical results don't remove uncertainty. So your p-values don't remove uncertainty from the conclusions you can draw. And so this is maybe a change in attitude rather than a change in, method or technique that's required. And this is told here very clearly in this quotation by Andrew Gelman. So as Sylvia mentioned, I have tried to implement these ideas in two books that I wrote, and chapter 6 in the purple book is covers similar topics to this talk. And then finally, I leave you with this cartoon, which suggests maybe that if you collect data in the right way about certain questions, then the result might be sometimes so clear that statistical significance tests aren't as important as they sometimes claim to be. And with that, I close, and sorry for overrunning. Thank you very much. Any questions?
Hi, everyone. If anyone got any questions, please do put them in the chat. And we've got one question already, Peter. And it was from Sylvie. And then you did touch on this a bit, but I don't know if you can say any more about how open science practice can overcome these pressures when the onus is still on researchers to report significance as an indicator of impact. And I guess in addition, I'd like, what open science platforms do you use? I've heard of Open Science Framework to post your code and things on, but I'd be interested to hear about what you use.
So there's the OSF, they're called the Open Science Foundation, where you can publish, for example, protocols for study before you carry out the study. So this is a version of announcing your methods before you do them, so you can't fish for statistical significance later. In terms of publishing, being transparent about your methods and publishing your data. So UCL, for example, has a data repository where you can publish your data, which might be your research data, so your actual, the thing you analyze, but it might also be other data, such as so what's called metadata, your questionnaires, and indeed your statistical code. So that's another possibility. The third one is that many journals now allow online supplements, and so these can also be used to provide more information. And it's troublesome because it's extra work for you. but it's very good for science, and that if people then want to either reproduce or replicate your study, they are in a better position to do so. So it's not enough to write in the paper, the data can be gotten from the principal investigator on request. That often doesn't work. So it's because 3 years later you might not find the data and so forth. So better to publish it, to think of that as part of publication. And I think there's maybe something for universities and funders to think about: do you need to fund explicitly the extra time these sort of practices require? Have I answered that question? Yeah.
Yeah, brilliantly. Thank you. And we've got a few more questions. Sarah's asking, does there need to be more funding available for replication studies, as it's not currently widely regarded as an attractive area to study, as there's so much emphasis on producing new results rather than checking previous results?
I don't know what to say except to agree. I mean, there's a little bit of drive now to do that. So these large scale replication attempts did get funded. But yeah, at the moment, they're the exception rather than the rule. So we don't know actually how many published research findings are false. And of course, that might differ by area. Yeah, totally agree.
Another question from Jack is there a suggested metric of uncertainty which might be worth considering when reporting results?
Yeah, so I guess my answer would be in specific cases there may well be. I mean, the p-value is actually a good indication of the compatibility of the data with a certain hypothesis, but the problem is that any statistical hypothesis test makes a lot of assumptions that are not necessarily testable, such as the data being unbiased, or the data collection having been done so that there's no bias in the analysis. For example, distributional assumptions about the variables that you cannot test and so forth. So I understand the desire for one number. This is it's good, it's useful, and it's useful in communicating and so forth. But actually, most of scientific progress doesn't work that way. You need to think about many different things and weigh up the evidence. And there's not necessarily always a mathematical way to come up with one number that summarizes strength of evidence. So you will find people who claim that. So sometimes people have suggested, well, instead of all this hypothesis testing, let's do Bayesian analysis. But I think you'll get into, and that has advantages and or strengths. But that does get you in. Ultimately, it gets you into the same kind of problems. So I don't know if you know these things. How big does a Bayes factor need to be for you to claim that it's important evidence? You get into the same question: do you make a binary decision or not? So I'm afraid I'm the opinion so far in my thinking about this that you actually need to have the attitude of, well, at the end of your study, you might still be uncertain, and there might not be one number that tells you exactly how good your methodology was. It's a bit too complicated for that.
Yeah, and actually you've brilliantly answered quite a few of the follow-up questions to that as well, that was specifically asked about Bayesian analysis as well. And other people are going to talk about confidence intervals and effect sizes as other ways of showing it. Would you agree that that's also another useful metric to perhaps use to help explain?
Yeah. So yes. Confidence intervals and effect sizes, and also confidence intervals of effect sizes, which is not always done. Absolutely. Well, on purpose in this talk, I didn't go into technically which analyses you could do beyond hypothesis testing, but those are two, and it depends a bit on what you're researching, obviously. But of course, some of the limitations are the same. So the confidence interval is only valid if your analysis is unbiased. So, the confidence interval of an observational study might be totally wrong if you have selection bias in the data. So you're improving, or you're addressing some limitations of hypothesis tests with these things, but you're not necessarily addressing all the problems with the current use. So, for example, the multiple testing problem, the confidence intervals and effect sizes won't get around that. If you're selecting the analysis you report by the effect size, you have exactly the same problem again as if you do it by p-value. So it solves something, or well, improves some things, but not others.
Brilliant. And I've got a question from Natalie about what your thoughts are on the use of negative control analyses in epidemiological studies. If you know what that is, I'm not sure what that is.
I'm not sure. Can the questioner explain?
Natalie, if you'd like to unmute yourself, and maybe that would be the quickest way of explaining what it is. But if not, no worries, we can move on to the next one. Is Natalie here still?
She has no microphone, she's just saying.
Oh, okay.
Maybe I can say I look this up, and if you want to write to me later, I'm very happy to think about it.
Brilliant, thank you, Peter. A few more just before. Do I have a couple?
I think
more one more.
Question.
Okay. So I'll just take this last one, maybe from Mohammed, who said he's seen some authors saying there was no association, to avoid saying there was no statistically significant association. Don't you think the former is even worse? If else, I guess how best can you describe a statistical significance?
Well, it's a little bit dangerous to answer it in general, because then you're just creating a new rule that, and one of the problems is, I think, that people like to follow easy rules and stop thinking about the data. But I mean, in general, say you observe a correlation of 0.3, give a confidence interval for the correlation to show how well have you estimated that thing that you're interested in. So, I mean, I think one thing, well, one way to think about these things, I think, is you always have something you're interested in measuring. And so if you calculate a correlation, you've actually measured a property of reality, but you want to know how well have you done that. And if you're convinced that everything else in your study is fine, so there's no selection bias, you've controlled for all the necessary confounders and what have you, then you'd still want to know, how much noise is there probably left in the data. So then the confidence interval can help you. So if your confidence interval is 0.29 to 0.31, that's a pretty good, you can be pretty confident that the correlation is about 0.3. But if the confidence interval is minus 0.5 to 0.9, then you've essentially no information, because almost any correlation that's plausible scientifically is compatible with the data. So that would be my way to think about it. So there have been guides on how to write about these things without falling into the usual traps, and I think I cite some of them. Happy to provide further if if people want to follow up. So that's useful, but it's I'd say it's the way of thinking about it and then writing about, not just having one formulation, but writing about it in the context of what you're studying intelligently, that might make the biggest difference.
Brilliant, thank you, Peter. So shall I pass over to you to wrap up? Apologies,
yeah.
1 o'clock right on the dot.
Yes, we're at 1 o'clock on the dot. Thanks very much, Peter and Ruth, for posing the questions. Thanks everyone for joining. Peter, there's such positive feedback from everyone in the chat, so I'd encourage you to look at it. Oliver put in the chat our feedback form, so if you could complete that, it takes literally a minute. We also have recordings of our previous webinars, and I will pop that in the chat too. You can also get in touch with us on arc.academy@ucl.ac.uk if you'd like to join our mailing list. Peter, thank you again for such an interesting, engaging and encouraging talk, I think, as well. And we're so glad to have welcomed you for this invited speaker seminar. So thank you very much, and thank you all for joining. I hope you all have a lovely day.